Before we proceed to the problems that we are going to solve, let's do some revision on single-stage equilibrium and multi-stage equilibrium of liquid-liquid extraction. Now, let's look at the schematic diagram of single-stage liquid-liquid extraction. Okay, so if the feed L0 and the solvent V2 are mixed, the resultant mixture has two liquid phases, which is called extract, which come from stream V1, and the raffinate, which come from stream L1. The composition of Y and X may be determined by the using of ternary diagram. So the ternary diagram that you're going to see in this problem is this type of ternary diagram. Now, let's look on the multi-stage liquid-liquid extraction schematic diagram. We call this multi-stage because you have more than one stages in the process. Because we have more than one stages in the process, the solvent stream is labeled as Vn plus 1 and the raffinate stream is labeled as Ln. Therefore, the composition in the solvent stream and the raffinate stream will be labeled as follows. The component in the solvent stream, which is Vn plus 1, are labeled as Yan plus 1 to represent the solute component, Ybn plus 1 to represent the diluent component, and Ycn plus 1 to represent the solvent component. Whereas the raffinate component are labeled as Xan to represent the solute component, Xbn to represent the diluent component, and the Xcn to label the solvent component. So, when you talk about multi-stage countercurrent extraction, the only difference from the single stage is this is only a single stage liquid-liquid extraction or single stage countercurrent extraction. So when you talk about multi-stage countercurrent extraction, you are looking at the bigger block diagram here. Okay, alright, so because both case for single stage and multi-stage countercurrent extraction, the types of graph can be given to you is this following graph. Okay, so this following graph. So there are two types of graph that you might get. The first one I have mentioned to you before, where you have two graphs arranged in parallel, and this one is the second type of graph, which only given to you one graph only. Okay, so just take a look on what we have here. Okay, so this is the type of graph. Okay, hold on. So this is the type of graph that you might get. Okay, so let's proceed to the questions that you would like to solve. Now, let's do the questions. In a chemical plant process, 1000 kg per hour of an acetic acid water solution containing 68% of acetic acid is being extracted countercurrently by pure isopropyl ether at the rate of 1000 kg per hour. And to reduce the acetic acid concentration to 4% in the raffinate, The ternary diagram of the acetic acid water isopropyl is given in the appendix. The first question is to sketch and label the schematic diagram of the system. The second question is to calculate the composition of the extract and raffinate. And the third question is to calculate the number of theoretical stages. To answer question number 1, which is to sketch and label the schematic diagram of the system, you need to draw the schematic diagram, which consists of 4 streams. So what streams do you have? You need to draw V1, Vn plus 1. You need to label V1 as your extract, Vn plus 1 as your solvent, L0 is your feed or fresh feed, and Ln as your raffinate. You just need to draw the block diagram of the multi-stage countercurrent extraction. You don't need to draw what's inside. Okay, by looking at the question, you are given 100 kg of acetic acid water solution. So you are given a mixture of acetic acid and water. Okay, and then when you read some more, you are also given pure isopropyl ether as your solvent. Okay, so in this case, you're going to label acetic acid as your solute because this is what you are interested in. Water is your diluent and pure isopropyl ether is your solvent. Okay, then 1000 kg of A plus B. So this is considered as the feed mass flow rate. Okay, so this is L0, which is given as 1000 kg per hour. And then it is mentioned also the solution consists of 60 weight % of acetic acid. 60 weight % of acetic acid is being extracted by pure isopropyl ether. So what we have here, the composition of A in the solution is only 60%. So you can label that information as 60 weight % of A here represent X A0. Okay, and then we also have some more information here where you are also given 1000 kg of pure isopropyl ether. Okay, and this isopropyl ether is pure. Therefore, you can say that for your solvent, YCN plus 1 is equal to 1 and Vn plus 1 is equal to 1000 kg per hour. Okay, and then the last information here, you are given the concentration of acetic acid should be reduced to 4 weight % in the raffinate. So, by assuming that the raffinate and the extract components are in equilibrium state, therefore we can write X AN is equal to 0.04. Okay, so we use a mass fraction in this calculation because X and Y in the schematic diagram represent the mass fraction of the system. Okay, so not to forget here, XA0 is equal to 0.6. Even though the value given here, which is 68% for acetic acid, but you should know that in the solution it only consists of acetic acid and water. Therefore, the balance of 48% will be for water. So you can also write this information where your XB0 is equal to 0.4, which represent 48% of water in the solution or in the feed. Now, let's put the information that we have in the schematic diagram. So we have XA0, which is equal to 0.6, XB0 equal to 0.4, and then we have L0. Okay, I just label here L0 equal to 1000, okay, kilogram per hour. And then we also given the solvent flow rate, which is Vn plus 1 is also equal 1000 kilogram per hour. And then we have XAN, which is given by 4%, which is 0.04. And then you are also given the solvent used here, which is pure. Therefore, YCN is equal to 1, and the solute in the solvent is 0. Okay, so in order for us to draw everything, okay, based on the data using the graph given to us, we at least need some information here. One, so let's assume the raffinate composition and the extract composition are in equilibrium, okay, in equilibrium state. Therefore, if they are in equilibrium, so look at our graph. Okay, if they are in equilibrium, so what we have here, okay, so remember this is equilibrium curve. If our extract and the raffinates are in equilibrium, the composition are equilibrium, therefore the raffinate position or points will lies on this particular equilibrium curve. Same thing with the extract. Okay, so the extract will lies on this extract layer. Okay, but if you don't assume your raffinate composition is at equilibrium, therefore it is not possible for you to assume the position or the location of your LN on this particular curve. It might be on the other side of the curve. Maybe it's inside or in the two faces area or in the single phase area. Okay, so because we assume that when L0, which is your feed, okay, mix with your solvent, okay, the two faces will be formed. Okay, so when the two faces will be formed, okay, and they are equilibrium, therefore the position of L and the rest of the L will be on this particular curve. Okay, okay, now look at question number 2 or part 2. So for the question number 2 or part 2, you need to calculate the composition of the extract and the raffinate. So we need to solve the composition of the raffinate and the composition of the extract. Okay, so we're going to do that now. Now let's do the material balance for our system. Okay, these are the mass balance on the system that we have. First, we just write the overall mass balance, which consists of L0 plus Vn plus 1, which is equal to Ln plus V1. So this part is the inlet stream, the mass balance, the total of the inlet, and this one is the total mass for the outlet. Okay, and both will give you the total for the mixture. Okay, and the second one is the mass balance for component A, which is XA0 multiplied by the flow rates of the feed, YA n plus 1 multiplied by the flow rates of the solvent, and XAN multiplied by the flow rates of the raffinate, YA1 multiplied by V1, which is the extract. Okay, so everything is equal to, okay, we need to have this one, M multiplied by XAM. Okay, so that is the composition for the mixture, solute, mass fraction of the mixture. So by looking at the schematic diagram, we have L0, we also have Vn plus 1. We don't have Ln, we don't have V1. And we can equate these two, which is L0 plus Vn plus 1 with equal to M, Okay, so if you can write the equation, it can be something like this. So this will give you, which is equal to L0 is 1000 plus 1000 from the solvent, which is equal to M. So your M is equal to 2000 kilogram per hour. So now let's look on what we have for the mass balance for component A. You have XA0, you have L0, you have YAN plus 1, you have Vn plus 1. Okay, you have XAN, but you don't have Ln. You also don't have YA1 and you don't have V1. You have M, but you don't have XAM. So now what you can do is to take a set of equation which is consists of this part of equation, which is equal to mx am. So now let's substitute the value that we have. XA0, which is given as 0.6 multiplied by L0, which is 1000. YAN is equal to 0 multiplied by Vn plus 1, which will give you 0. Now it is equal to, equal to M. You know M already, which is 2000, and then multiply by XAM, which is your unknown. Now you can solve for your XAM, which is equal to 600 divided by 2000. That will give you 0.3. So the mass fraction of the mixture, which is XAM, is 0.3. So the value is not more than 1. Therefore, for the time being, we're going to accept this value of XAM. Okay, now we have done using the overall mass balance and mass balance for component A. So now let's look on the mass balance for component C. Now let's look on the mass balance for component C. So this is the mass balance for component C. Now let's look on what do we have in the information on the schematic diagram that we have drawn, and try to substitute here whether we can solve something from this particular mass balance for component C. Okay, now let's go on with that substitution. Take a look at the data that we have. Do we have XC0? Yes, XC0, we have XC0, which is equal to 0, and L0, we have that already, which is 1000. And then YCN, from the schematic diagram, we have equal to 1, and Vn plus 1 is 1000. XCN, we have that 0.0, we don't have that information, and then we also don't have that Ln. YC1 also we don't have, and V1 also we don't have, but we have M and we don't have XCM. Okay, now let's do the substitution. XC0, which is equal to 0, anything multiplied with 0 is 0, and then you have YCN plus 1, which is 1, multiply with Vn plus 1, which is 1000. Okay, and then equal to, okay, you don't have that information, and then you also have this part, which is equal to M, which is M just now we calculated, which is 2000, and then we also don't know XCM. Okay, so it is obvious that we have this particular equation, okay, together with that particular equation. Alright, so what we have here, we can solve for the XCM, okay, which is XCM is equal to 1000 divided by 2000. That will give you 0.5 for the mass fraction for the mixture. So we have something or some information here to work with. Okay, now we have information. I think we have enough information, but you can check whether we need some more calculation using the mass balance or not, in order for us to calculate, to get the information or to answer the questions. Okay, so let's look on what we have here. Okay, alright, so I'm going to simplify the information first before we plot on the graph. Okay, so by looking at the graph, okay, so the graph consists of y-axis and x-axis. So the y-axis represented by the mass percent or mole fraction. Okay, in this part you have mass percent. Okay, right, here you have mass percent also. So for the x-axis you have the mass percent of solute, and for y-axis you have mass percent of your solvent. Okay, so what do you need in this particular question? So let's do some brief some summary on what we have. Okay, now so let's say we have the composition for A and C. So it is obvious that your C is equal to 0. Okay, so you just take the components. Okay, just take the components of A and C. Okay, A and C, because your graph is C versus A. Okay, so you have one coordinates for L0. So you can plot the L0, which is XA0 is equal to 0.6. So this is 60% of A. Okay, and then for your C it is 0, therefore your L0 lies at this particular point. Okay, next is to look at your extract. Okay, look at your extract. Okay, because you have a complete information. So your information here consists of A, and C. So you can plot the coordinates for Vn plus 1. So the coordinate of Vn plus 1, when your A is 0, your C is 1. So the position of Vn plus 1 is here. Okay. And then, okay, you also given the coordinates for your mixture. Okay, coordinates for your mixture. So you are given XAM, which is 0.3, and XCM, which is 0.5. So now in the graph, okay, you have XAM, which is 30%. So you just go this way, okay, at 0.3 and meet with 0.5. Okay, so you have this particular position, okay, in your graph. All right, so you have these particular coordinates for M. So just label this point as M, this one as your L naught. Here is your Vn plus 1. Okay, so what about your V1? So we don't have enough information on V1 yet. Okay, and we have some information for the raffinate. Okay, since we assume that the raffinate composition is equilibrium, therefore XAN, which is given by a value of just now 0.04. Okay, so you go here, the XAN, so you have 0.1 here, so you just take 2 box. So you're going to draw, okay, something like this. So let me enlarge this graph, okay, and then put here. Okay, so you have 0.04. So this is 0.01. So 0.04, you have 1, 2, 3, 4, 5 boxes. So 0.04 is here. Okay, but since it is equilibrium, you can just extend the line. Okay, just extend the line. So let me show you here. So you just extend this line, and then the position of L naught is where the XAN meet with the equilibrium curve. Okay, so this will be the position of Ln. Okay, so this is the position of Ln. Then the next step to do is to understand how to get the reference point, okay, or the operating point, and how to get the reference point or operating point you label as a triangle. Okay, so how do you get this reference point? The reference point is when you draw a line. Okay, you draw 2 lines between L naught V1, and then you draw another line which is Ln and Vn plus 1. Okay, so when these 2 lines intercept, okay, that line, that point is called the operating points or reference point. Okay, and another other lines that you need to know to draw is the line between L naught and Vn plus 1. Then you need to know to draw the line between L and with a V1. Okay, so the intersection between L1, the L1 V1 Vn plus 1 and Ln V1 will give you the point where you get your M. Okay, to get your M coordinates. Alright, so later you're going to calculate the number of stages. So the number of stages is when you have when you can draw a line or tie line between L1, V1, L2, L2, V2, L3, V3. Okay, all right, so this is what we're going to do next. Okay, based on the data that we have, okay, you can plot the coordinates for M, okay, the coordinates for your feed, which is L0, and the coordinate for your solvent, which is Vn plus 1. Okay, so you need to have this information, the three coordinates that you have, which is M, L0, and Vn plus 1. You plot on the graph, okay, and then draw the three lines involved, which is the two lines that will intercept with your M, okay, and then the other two lines that will give you the interception to give you the operating point or reference point. Okay, so from the reference point that you develop and from the two lines that intercept at M, you will be able to determine the value for V1. So from the graph that you have, you can look through the solution in the other video. Okay, so please look at the other video and then you can get the final answer here. Okay, so from the graph that you have plotted, which consists of the point M, L0, and Vn plus 1, you should be able to get the value or the position for V1, which is your extract. So from the graph, you are able to get the YA1 or the mass fraction of the solute at your extract. So in that graph, you get the position, the location of YA1 at 36%, which is 0.36 mass fraction. Okay, and then since the graph will give you the value of solute and the solvent, you can also get the value of your solvent, which is at 0.6, or from the graph you get the position is at 60%. Okay, so from here you can calculate the composition of B or diluent for each of these stream by having the two at the two composition, and then make sure that you have 1 minus the two composition that you're talking about. For example, we have how to calculate YB1 is to have 1 minus YA1 plus YC1. Okay, remember the mole fraction that you have done before. You get YA1 plus YB1 plus YC1 at the stream that you're talking about will always equal to 1, not more than 1, not less than 1. It should be equal to 1. Okay.